So let's talk about the potential of a charged conductor. Now, when you're thinking about electric fields or the electric potential of a conductor, I want you to thoroughly understand what's going on in this particular situation. Okay, we're dealing with an electrostatic condition right now. Later on, we're going to get to currents, but for right now, it's an electrostatic condition, and you have to understand that and what that means, or none of this is really going to make sense. It means there's no flow of charge anymore. Now, at first, there had to be a flow of charge. We got a charge distribution because charges were moved to a particular place, so you had currents. But now we're looking at a situation where charges aren't moving anymore. Now that's why if you have a conductor, there cannot be an electric field inside the conductor. You can't have an electric field inside a conductor if you have an electrostatic condition. Because if I've got, some chunk of metal, maybe we deal with spheres a lot, so here's a spherical piece of metal. And let's say, let's make this a cross section, and let's say I put a net positive charge inside. Well, in a conductor, charges are free to move. And so these guys are going to apply forces to each other, and because they're free to move, they're going to move, and so it's not going to be an electrostatic condition. This guy, let's take a look at these two guys. They apply equal and opposite forces to each other, and it's always going to be outwards, right? They're going to be repelled. So you're going to get a flow of charge until the charges stop moving, and eventually it's going to turn into this. It has to. Here's my sphere again in cross section, and all these charges will go to the outside where they're trapped. Okay, now, by the way, it is possible to make charge flow off of this surface if you get a high enough voltage. Okay, but it's really high. And that's when you get lightning bolts and stuff. And we're not going to worry about that right now. Just assume that when you have a charged conducting material, that once the charges get to the surface, they're trapped. Okay? Now, these guys are still applying forces to each other, right? Let's look at this in cross section again. But these two guys are applying forces to each other. So this guy is repelled and this guy's repelled, but this guy is repelling it too. And they're balancing each other out. Okay, and now they want to adjust themselves, and these charges are going to adjust themselves so that when they stop moving, you're going to have what's called and we talked about this before. This surface is all going to be at the same voltage. The surface of a conductor must be, am I on camera? Yeah, must be an equipotential surface. Now this, of course, is assuming that we have an electrostatic condition. Now, why? Why is the surface of a conductor an equipotential surface? Because if there was a voltage difference, let's take a look at this location and this location. We'll call this A and this B. If there was a potential difference between A and B, charge would flow. You'd have a current. Okay? Another way of looking at it in terms of the electric field is that we said that a potential difference is equal to negative E dot ds. Okay? And so in other words, there would have to be an electric field times the displacement between A and B, but that's not going to happen, because what happens here is that these electric field lines come off perpendicular to the surface. Okay, so electric field lines, we talked about this before. Electric field lines come off perpendicular to the surface of a conductor. They have to if you have an electrostatic condition. Because if the electric field came off with a component parallel to the surface of the conductor, what's going to happen? Charge is going to flow. It's going to move the charge on the surface. Well, if you have moving charges on the surface, you no longer have an electrostatic condition. So if you've got an electrostatic condition, and that's the big thing, you have to understand that, then because it's a conductor, because charges can flow, then the electric field cannot exist within the interior of your conductor, and it has to come off perpendicular to the surface, and the surface is an equal potential surface. And because these ideas are all related to each other. The fact that these electric field lines are perpendicular to the surface is why there is no electric field at anywhere parallel to the surface. So if I move along the surface, okay, everywhere the electric field is perpendicular to my displacement, isn't it? Everywhere along the surface of a conductor and under electrostatic condition, okay, the electric field is perpendicular to my displacement along that surface. So when I get to my definition of potential difference, the electric field and my displacement are always perpendicular to each other. Well, what happens if two vectors are perpendicular to each other when you take their dot product? You get zero. So there is no potential difference between A and B. Okay? Now, by the way, this is true even if this conducting material is hollow. If I have just an empty cavity in here, let's put some kind of hole in it. This is empty space inside here. Whoops. Well, if I deposited some positive charge along the surface of that, it's going to apply an electric field. Well, this electric field has to terminate somewhere, and it's therefore going to apply an electric field inside the material itself and cause charge to flow. So it's not electrostatic anymore. And so what that means is that even if you have an empty hole or a cavity inside your conductor, now I said empty. Remember the take-home test problem you're working? You've got a metal shell, right? Which problem was that?
6.
Number 6, there was a metal shell, and inside there was a metal sphere with charge on it. So inside that metal shell, it's not empty. There's a charge in there, so it's a different situation. But in this situation, if I just carve out some empty space, there is not going to be any charge inside there. All the charge, all the net charge on a conductor has to be on the surface. Okay. Now, this is a nice symmetric sphere. What would happen if I made it a teardrop shape? What's going to happen? How are these charges going to adjust themselves? Okay. And I want you to really grasp this conceptually. You can do it. Let's say I have a shape like this, a teardrop shape, and it's all metal. And let's say I deposit some charge on it. Okay. Now, the question is, what's the charge distribution going to look like? Well, I want you to think about the charge that would be right here. Okay? Now you got all this charge. Do you see that you've got all these charges to the left, but look at this guy. It's got no charges to the right. So it's going to feel more force from these guys than it feels, over here. So what happens is that all of these guys, they crowd the charge towards that point. So what happens is that if you have a pointed area like this, or a surface that kind of comes to a point, the charge gets smushed over there. Now, this was a big debate, by the way, between Benjamin Franklin and Europeans, physicists, about what would make the best, what do you call this? It attracts lightning, it keeps lightning from striking a building. Lightning rod. What would make the best kind of lightning rod? Something that comes to a sharp point or something that's round. And the Europeans thought that you should make a lightning rod that was just a kind of a ball shape like this. And this would be the wire, and you would have this big ball of metal. And Benjamin Franklin said, no, it should come to a point. So you should have, some sharp point like this with a lightning rod that looks like that. Now, it turns out that Benjamin Franklin was right. Yeah. USA. All right. Well, that was I think he did this before there was America. We were still part of England. But still, I don't know. I could be wrong on that. We could look those dates up. But and here's why. And they were just figuring this stuff out. The fact that the charges will crowd around this point means that the electric field at this point is much more intense. Okay? Now, along this shape, remember, the field lines are still coming off of it 90 degrees to the surface. If I took a microscope and looked at the electric fields coming off, even that very point at the end, the electric fields are coming off perpendicularly to the surface. But the field lines, because the charge is more crowded, the field lines are more crowded. But look at it this way. Let's take a look at these field lines.
Can you tell us why it's more crowded down there again?
Yes. I'll give you another explanation why. Well, the fact is that these guys this guy feels a push from this charge and a push from this charge. But the closer you get to the end, the less charge there is to your right. So these guys are going to have a net force pushing, before it's electrostatic, they're going to have a net force that's going to crowd you over there. Now, at some point, you get so crowded that the attractive force of the metal is just going to hold you on there. But another way to look at it is this. You see these field lines, how fast they're spreading apart? The tip here almost acts like a point charge. Whereas when you're close to the edge over here, I mean not to the edge, when you're in this part right here, the field lines don't spread out as fast. So now let's take a positive test charge and push it to the surface. We've said that the surface of a conductor is an equipotential surface. That is, the amount of work it takes to deposit a charge to that surface is the same no matter where on the surface you end up. I can take a positive test charge, here's my little Q naught, and I can push it against the electric field to there. And if I add up all the work it took to do that, it's the same as the amount of work it takes to go here, or here, or here, anywhere on that surface. Well, but look, if I'm out here, look at this, look at the field due to these charges on the tip. The field is spreading out. The field is quite weak out here compared to over here. Here, the field lines are not spreading out as fast, so the field is stronger here than it is over here. It's easier to push this again, so I'm not doing as much work as I approach this. Well, you got to make up for that. You got to make up for that, because what happens is that the field line, field lines close to this have to become much closer together, much stronger, to make up for the fact that they were much weaker further away. So as I push this against here, I'm going to push it against it, and I'm not much work, not much work, not much work. Oh, lots of work, lots of work. Okay, I just did a certain amount of work to get it there. Well, over here, it's kind of a lot of work, kind of a lot of work, kind of a lot of work, kind of a lot of work. A little bit harder, but not much, but boom. So when I add up the amount of work it took to approach it from infinity this way and from infinity this way, they have to add up to the same amount of work per unit charge. And thus, the electric field, field lines, because they spread out faster at a tip, the field has to make up for it by being very much stronger close to the tip, which means the charges have to be much more crowded. So that's one way to look at it. So you can think of it in terms of these guys jostling each other until they reach equilibrium. Each little charge has no net force on it anymore. And you can look at it in terms of how much work I got to do to place a charge, a test charge on the surface moving from infinity all the way to that surface. It has to be the same amount of work per unit charge, which means that the charge is going to be more crowded at the tip. If the voltage was, if there was a potential difference between this part of the surface and this part of the surface, that would drive a current across the surface that would bring it to equilibrium. So all of this is contingent on the fact that this is an electrostatic condition. Okay, so that's what's going on here. Definitely, read the book, and it does a good job of explaining this as well. But here's the thing, what you have to do to master electromagnetism is you have to imagine what's going to happen to a freely moving charged particle in this situation. If I'm a freely moving test charge, what's going to happen in order to put me into equilibrium? There's no, for me to stop, not to flow. Okay, and so it takes a little while, to master that, but you will, hopefully.